Welcome everyone. In today's session, we are going to explore association rules in data analytics. This method helps us uncover hidden relationships between variables in large datasets. It's commonly known through applications like market basket analysis, for example, finding that customers who buy milk also tend to buy other items like cheese and butter. My goal is to show you how these rules work, how we measure their strengths using statistical metrics, and how the same concept can be applied not only in retail but also in fields like finance, healthcare, and even engineering. Let's begin with what association rule mining actually is. It identifies frequent co-occurrences among items or variables, basically patterns that say if A occurs, then B is likely to occur. These are expressed as if-then relationships. For example, in market basket analysis, we could say if somebody buys milk and cheese, then the probability of buying butter increases. This approach is extremely powerful because it allows us to extract hidden correlations, dependencies, and behavioral trends directly from data. So we don't need to make any assumptions and basically we don't need to use any specific model. Association rule mining is used across many industries. In retail and marketing, it powers market basket analysis. The classic example is if a customer buys milk, they often buy egg and cheese. Retailers use this insight for store layout, cross-selling, and product recommendations. In finance and banking, association rules play a crucial role in identifying relationships among transactions, account activities, and customer behaviors. For example, banks can detect fraudulent transactions by recognizing unusual combinations of activities that rarely occur together, such as high-value transfers followed immediately by ATM withdrawals in distant locations. They are also used to segment customers to design personalized financial products. How it is done? By linking patterns of spending, loan types, and repayment histories. So as in retail, association rules help financial institutions make smarter data-driven decisions. In healthcare, it helps uncover relationships between symptoms, diseases, and treatments. For instance, it can identify patterns like patients showing fatigue and joint pain are likely to have anemia, or certain drug combinations increase the chance of side effects. These insights allow researchers and clinicians to improve diagnosis accuracy and treatment planning. Essentially, the algorithm acts like a data-driven researcher, analyzing thousands of medical records to find meaningful connections that may not be obvious to traditional analysis. In manufacturing and supply chain management, the same principles apply to operational data. For example, it can reveal which types of equipment failures tend to occur together. Say, when a motor overheats, a bearing failure often follows. They can also uncover patterns that lead to supply chain delays, like specific combinations of suppliers, materials, and routes. By understanding these co-occurrences, managers can design preventive maintenance schedules and optimize logistics to avoid cascading failures and inefficiencies. In civil and transportation engineering, association rule mining is equally powerful. It can connect diverse data sources, for example, materials, construction practices, environmental conditions, and performance outcomes to reveal patterns. Um, in an engineering example, let's assume that pavements with high wrap content or high recycled material content and low binder viscosity are more likely to experience cracking. By identifying such rules, we can enhance material selection, design specifications, and maintenance planning. Ultimately, these data-driven insights help engineers make decisions that improve infrastructure performance and longevity. Now that we understand what association rules are, let's discuss how we evaluate them. We don't just look at whether two items appear together. We need a way to quantify how strong or meaningful that relationship is. That's where these key metrics come in: support, confidence, lift, conviction, and leverage. And on this slide, I'm going to spend a quite bit of time to explain all these key metrics. Each tells us something different about how important a rule might be. Let's start with support. Support simply measures how often two items appear together in our dataset. So this means we are calculating the probability that both A and B occur at the same time. For example, if out of 100 transactions, 20 include both milk and cheese, the support is 0.2 or 20%. Support helps us filter out rules that are too rare to be meaningful. If something only happens once or twice in a massive dataset, it might not be worth considering, even if it looks statistically interesting. Next is confidence. Confidence measures how reliable a rule is. It's the conditional probability that a customer buys B given that they already bought A. So if 80% of people who buy milk also buy eggs, the confidence of the rule if milk then eggs is 0.8. Confidence is intuitive. It tells us how often the rule holds true. But we should be careful. A high confidence doesn't necessarily mean a strong relationship. If eggs are already very common in the dataset, we might see high confidence just by coincidence. That's why we look at lift. Lift measures whether the presence of A actually increases the likelihood of B. So if lift equals 1, that means A and B are independent. They have no effect on each other. If lift is greater than 1, then A and B occur together more often than expected by chance. This indicates a positive correlation. If lift is less than 1, they occur together less often than expected, a negative correlation. For instance, a lift of 2 means the items co-occur twice as frequently as random chance would suggest. So lift is one of the most useful metrics for discovering truly interesting associations. Now let's talk about leverage. Leverage tells us how much the actual co-occurrence of A and B differs from what we would expect if they were independent. Um, Leverage can be positive, zero, or negative. A value of 0 means no relationship. They occur exactly as often as expected. A positive value means A and B appear together more than we would expect. And the negative value means they co-occur less than expected. Think of leverage as the absolute difference between reality and randomness. It tells you how much more often a rule happens than it should by chance. And now let's talk about conviction. Conviction measures how strongly A implies B, but it also takes into account how often the rule fails. Um, this one is a bit more abstract, but it is very helpful when you are analyzing predictive rules. If conviction equals 1, A and B are independent. The higher the conviction, the stronger the implication. For example, a conviction of 3 means the rule A implies B fails about 3 times less often than you would expect by chance. Now, when evaluating rules, you rarely look at just one metric. You kind of look at a combination of different metrics. Support tells you if a rule is frequent enough to matter. Confidence tells you how reliable it is. Lift checks whether the relationship is genuine. Leverage shows how far it deviates from independence, and conviction captures predictive strength and reliability. A strong rule typically has high support, so it is common, high confidence, so it is reliable, and lift significantly greater than 1, so it is truly dependent. When these conditions are met, we can be confident that the association is not random. It reflects a real pattern in the data. Here is a simple retail example. Out of 10 transactions, 5 include all 3 items. So transaction 1, 2, 3, 4, and 5, they include all 3 items, milk, butter, and cheese. And other transactions, you see what items are included in those transactions. For example, transaction 6, it includes milk and butter, but does not include cheese. So let's use those metrics on this example and see if there are any relationships between the items. In this example, the rule that we would like to evaluate is if milk and butter, then cheese. In other words, how likely the purchase of milk and butter can result in the purchase of cheese. So we start with calculating all those metrics. The probability of A happens, the purchase of milk and butter, is 6. So we had 10 total transactions. So the probability is 6 out of 10, and that is 0.6. The probability of B occurs, B is just the purchase of cheese, and that is 5 out of 10, which makes the probability of 0.5. And by using all those metrics, so basically you can see that the probability of all 3 items together is 5 out of 10, 0.5. So If you use all those formulas given in the previous table, you can calculate the metrics, statistical metrics, and it will give you support equals 0.5 or 50%, confidence is 0.3, lift is 1.67, leverage 0.2, and conviction about 3. So how to interpret this? There is a strong rule because lift is 1.67 greater than 1 and conviction is 3, about 3. These two kind of indicate a meaningful positive association. In other words, when milk and butter are purchased together, cheese is bought 80% of the time and much more often than random chance would suggest. This supports bundling, co-placement, or inventory planning decisions. Now let's apply the same concept to a civil engineering dataset. In this dataset, we have a pavement data, and let's say that we have collected data on 10 different pavement sections, and the information that we collected is about the percentage of the recycled material used in the pavement, the airward content of the pavement, and the severity of cracking. So in section 1, for example, you can see that high wrap content is used, basically probably more than 40% reclaimed asphalt pavement material, and high airward content, probably more than 7-8%, and we also had a severe cracking condition. So we collected all this from different sections, and this is the table that we have. So you can pause the video and kind of calculate all those metrics and see if there is a association between having high wrap and high airward and severe cracking. So basically the rule that we are interested to evaluate is if high wrap and high airwards, then severe cracking. If you do the math and determine all those metrics, and the rule, as I mentioned, is if high wrap and high airwards, then severe cracking, the probability of having both high wrap and high airwards, this is 5 sections out of 10 sections, so the probability is 0.5 or 50%. The probability of having severe cracking, that's 4 out of 10, that's 40%. And both conditions, A and B together, having both high wrap and high airwards, as well as severe cracking, that is again 4 out of 10, that's 40%. With those, you can determine support, which is 40%, confidence is 80%, lift is 2, leverage is 0.2, and conviction is 3. So basically there is a strong positive associations. Pavements with both high wrap and high airwards are twice as likely to exhibit severe cracking compared to random chance. Lift is 2 here, so there is a strong positive associations, and basically with 80% confidence. So in summary, association rule mining is a data-driven approach to uncovering hidden relationships in large datasets. It's widely used from retail to finance and increasingly in engineering to identify combinations of factors that lead to specific outcomes. We evaluate each rule using quantitative metrics like support, confidence, and lift to separate real associations from noise. By combining engineering knowledge, With these analytical tools, we can make more informed, evidence-based decisions that improve design, safety, and sustainability.